tell you something about ideas that I've had for about a decade concerning cosmology and our place in the universe. Now, I want to show some pictures, and I hope that you can see these properly. When I show this picture here, I can't... Yes, I think I can see what I'm showing.
Yes, sir.
Can you see that?
Yep.
You can. And can you see, is it the right way around? So I want to make sure that this is the right-hand side over here.
Yes,
Or is
sir.
it the left
Yeah, the
side?
green lines, we can see that.
But can you see it on the right?
Yes.
Okay, so the words are the right way around. When I see the words, they're backwards, but they will be all right for you, okay?
Okay.
That's fine. Now this picture indicates the current picture of cosmology. This is meant to be the universe. You have to imagine that the picture is four-dimensional, but I can't draw four dimensions. But the time is going up the picture. So this indicates a section through the picture, and as time progresses, that section goes up. You have to think of this as three-dimensional space, and so you only see one dimension this way, but you have to imagine there are three of them. And that is the Big Bang at the beginning, the idea goes, and then as time progresses, the universe expands, it slows down a bit, and then it is accelerating in its expansion. This is the presence of what we call lambda, or what people call dark energy. I don't like the term dark energy, I think it's misleading. The lambda was something introduced by Einstein a long time ago, in 1917. His general relativity was in 1915, that was just 100 years ago, and he then, a couple of years later, introduced this term, which gives rise to this expansion that we see now. He thought it was a mistake to introduce that term, but it turns out he was right all the time, because this expansion is an observed thing, the exponential expansion that we see. Now in this picture, the space is rather ambiguous the way I've drawn it, because we don't know whether it closes up at the back or not. See, I have this kind of frilly stuff at the back here, which to indicate that we don't know whether the universe is closed or open. People tend to say that it's open because it's very close, the geometry is very close to being flat Euclidean geometry, but that might not be right. It might close up, it might be open. Now, in the lecture I want to give you today, it doesn't actually make any difference whether it's closed or open, so you can take your own view about this. If it is closed, it is a very, very big universe. It doesn't close for a long time. Okay, so that is the standard picture, and I wanted to indicate also the different geometries that people usually consider. These are pictures by the Dutch artists M.C. Escher. Now, I hope this is the right way around. The K is less than 0. That means this is the... Well, let's take that case first. This is the flat space, which means Euclidean geometry, and the universe would be open. This is a closed case, which is like a sphere, so the universe would be spatially closed up on itself. And this is what's called the hyperbolic case, which is even more open, if you like, than this case. The geometry is very nicely illustrated by Escher, that these angels and devils, I hope you can see, I have a bigger picture later on, but the whole geometry is represented in this finite region. So you even have infinity represented by a boundary in this geometry. This will be important for what I want to say later, that you can actually picture the whole universe right out to infinity as though it was a finite region. This is what's called a conformal map. The devils and the angels are squashed down as they get closer and closer to the boundary, which represents infinity. But the squashing is such that it's the same in both directions. So the amount of squashing in this direction is the same as in that direction. It's what's called the conformal map. That means that shapes, very small shapes, are accurately represented, even though they maybe look very small in the picture. So you expand it out uniformly, and you will see that the angels and devils look very much like the ones in the middle. And they think they're the same size as the ones in the middle, because their geometry expands this out, make this is infinity. So that will be a useful idea for what I want to say later on. So let's keep that picture, and I will mention some of these things later on. Okay, let me return to this picture I had before. Now I think I want the green line on this side. So that's the green on the right-hand side. That's time is going up the picture. Now, was there a question?
No.
Okay. You see at the beginning what's called the Big Bang. Now this is meant to be a singularity, so that the geometry becomes, well, curvatures become infinite, and the equations give up. And Einstein didn't like that very much, but he became persuaded that his equations did give you an infinite beginning like this. Now, there is something that is, people might say there's something missing from this picture, which is the thing called inflation. Now, inflation is something which is supposed to have taken place very, very early on in the universe, between, well, about 10 to the minus 36 and 10 to the minus 33 seconds, which is a very, very tiny length of time. So you might say, people might complain, well, my picture doesn't put inflation in here, but then maybe I did put inflation in, but it's so tucked into that little black spot, you wouldn't see it. So let me show you what you would need in order to see what's going on. You would need a very powerful magnifying glass, and this magnifying glass will give you a picture of what's going on. Well, what do you see? According to the current picture of cosmology, you will see this is the magnifying glass, that's the handle of the magnifying glass, and it looks very much like the picture that we see now. So we have this, what's called an exponential expansion. That means it's self-similar, it's similar to itself. No matter how much you magnify it, the picture looks very much the same. Now, it looks also very much like the exponential expansion that we now see. So people say in current cosmology that not only is the universe going to have this exponential expansion in the remote future, I should say that we are now somewhere about here. So we are beginning to sense this expansion. But this keeps on going forever, is the view. And this exponential expansion, according to the inflation, is something which happened before, very, very early in the universe. Now, there are various reasons for inflation. I happen not to believe it. I think that inflation is not correct, that it did not take place, but there's something very much like inflation, because inflation is needed to explain certain features of the universe which are very hard to explain otherwise. One of these is that the irregularities that we see, and I'll come to this shortly, when I talk about the microwave background, that there are certain things which are independent of the scale. And the only way that people can explain that in current cosmology is that this inflation takes place. Now, one of the reasons, that actually turns out to be not a bad reason, but one of the reasons people introduced inflation originally is that they couldn't understand why the universe seemed to be very smooth and very, very close to being flat. And they thought that the universe might have started very complicated, and then it stretched out by this inflation, and it was made to look very smooth. Now, I don't think that is the correct explanation, and I'll try to give a reason for thinking this later on, but let me come to that later. For the moment, what I want to describe is my own view, and my own view I will say in more detail shortly. This picture is not a bad picture for what I'm calling one eon of the succession of such things which will continue indefinitely. Now I have to understand, to explain how this works, by doing two mathematical tricks. The first of these tricks is to stretch out the Big Bang. Well, that's the second trick. The first trick will be squash down infinity. That's the one that I talked about in my Escher picture. In the Escher picture, and let me show you a big one, a big version of that. Here we have the same picture I showed you before, slightly bigger. You can see the angels and the devils, and infinity is represented as a finite boundary. Now, it's also a conformal map, so the stretching and the squashing are uniform in different directions. Now, I want to use the same trick to our universe, but not spatially. This is a spatial geometry, but this is the temporal geometry. So I'm going out in the future direction, and I'm going to use this trick to apply it to the very distant future. So the idea is to squash infinity down to make it to a flat, to a boundary to the future. So that's one trick. And the other trick will be the opposite trick. I will stretch out the Big Bang so that it's not a singularity anymore. So those are the two tricks. And I want to have my picture of the universe a bit smaller to make it a little clearer how these tricks work. One trick, as I say, is to squash infinity, so it's a finite boundary, very much like what we have in this picture, finite boundary, and I stretch out the Big Bang to make that another finite boundary. Now I want to say something about these two tricks. In our present ideas about cosmology, if we have this term lambda, Einstein introduced in 1917, and it seems to explain this exponential expansion here, then this trick works for almost any universe. If you take any model of the universe, which has this exponential expansion, has the lambda in it, and it can be irregular in all sorts of complicated ways, you could still do this trick to make finite the future finite like this. So that works. What about the other trick, stretching the Big Bang out? That is a very, very strong condition. It hardly ever works. But what I'm trying to argue is that we want it to work, and we want it to work because of something which is very fundamental in physics, which I'll come to in a minute. But before going to that, I want to explain what is outrageous about my theory. So far, this is not outrageous. This is just two mathematical tricks. I can squash infinity down, I can stretch the Big Bang out, and if it's a Big Bang for all the standard cosmologies, the ones that people looked at, because the universe seemed to be very uniform, all those cosmologies, yes, you can do this trick. And so there's nothing outrageous about this. This is just a standard thing you can do. What is outrageous is the following. I want to say that, in a certain sense, that the trick is really that the infinite universe really has a boundary like this, and this infinite Big Bang really can be stretched out, and it makes physical sense. And that this boundary fitted on to the infinity of a previous eon. So this is what I call an eon. There will be another eon afterwards. There was an eon prior to ours, and these continue indefinitely in both directions. I feel there may be something a little in common with certain Indian philosophical ideas, where you have the universe going through sessions like this. What's a bit special about it here is that the time scale is, in a sense, infinite. It's infinite, but in a sense we don't mind, and I'll try to explain that later on. So this is the picture, which I call conformal cyclic cosmology. I want to indicate that there are observational implications of this scheme, and that these observational implications, there is some indication that it may well be true. Now this, I should say, is not accepted by current cosmologists. They find this is too outrageous. However, a lot of things that they do are pretty outrageous too. The inflation model is already a very extraordinary idea, and it has to depend on certain physical ideas which we have no other reason to believe in. Whereas this ties a lot of things about physics together. And the most important thing that it ties together is to do with what's called the second law of thermodynamics. I should contrast this model with a much older model, which was introduced by Friedman originally, and then by Tolman. And this is a model in which the universe is spatially closed. So this is the space going around horizontally again, and you see the space sections are closed up, like the spherical model. And here it's Big Bang, and then the universe doesn't keep expanding, it collapses, and then it bounces and produces another cycle like this. So this model is quite an old one. The American cosmologist Tolman wanted to incorporate second law of thermodynamics, because the second law tells us that there is something called entropy, which is a measure of randomness in the world, and this entropy is increasing with time. And how do you have entropy increasing when you have a cyclic model like this? But he suggested that the model wasn't exactly cyclic, and this was his way of doing it. Now, why do we believe that there is a Big Bang anyway? One of the reasons comes from Einstein's equations, which tell you that these models are the ones that satisfy Einstein's equations, and they have Big Bangs in them, which he didn't like originally, but he had to get converted to the idea. But observationally, well, we see that the universe is expanding. If it's expanding, what happened in the very early stages? Well, when what's called the microwave background was discovered, this was about 50 years ago, when people realized that there was this radiation coming in from all directions. This radiation is electromagnetic radiation, so it's like light, but very much longer wavelength. So it's microwaves, and this radiation is seen to come from all directions in a uniform way. It's not completely uniform, and this is because the Earth is moving with respect to this radiation, and the direction of the Earth's motion gives it slightly warmer in the directions we're moving and slightly cooler in the direction we are moving away from, but that can be easily understood. However, if you correct for that, you find this radiation is very, very uniform in temperature over the whole sky, to about 1 part in 100,000. So the temperature is very uniform. Now, the temperature also has a very particular characteristic, which is shown by this graph here. This is what's called a Planck spectrum, that curve. What we have here is the frequency in this direction, so this is the frequency increasing this way. This is the intensity for different frequencies. And what they find is that the intensity follows this curve very precisely. And this curve is what is called the Planck curve, and I'll say the importance of that in a minute, but it's very close. The observations are very close to this curve. These are error bars here, and the error bars are exaggerated by a factor of 500. So you have to imagine that the error bars are much smaller, by a factor of 500. So even where they're at their biggest, the errors are within the thickness of the incline. So the precision in this, the agreement with this Planck curve and the data is very, very strong. Now what does that mean? And what does the Planck curve mean? Well, it was introduced by Max Planck at the turn of the